We want to discuss now how, given the local form, the zeros of a polynomial, we can construct the global form. Okay, so this is the opposite. Last lecture we did the global form, how to find the local form so we could find the zeros. Now we're going to be given the zeros and we want to construct a polynomial. Okay, so again, I just want to go back and review. The local form is the factored form, and we use this to find the zeros. And the global form is basically the definition. Okay? So here's find a polynomial function of degree 2 having zeros. X equals 2 and x equals minus 3. 2 and minus 3 are the zeros. Okay, so this is what I give you. It's a polynomial of degree 2, so it has 2 zeros. Okay? Degree 2 means n is 2, and my zeros are 2 and minus 3. Okay, good. So how do we go? Well, my x1 is 2, right? My first zero is 2. Well, it doesn't matter the order. So my first one is 2. My second one is minus 3. Again, you can either one is 1, fine. So here's my formula. There's my local form. So a second order polynomial. This is why I like to keep track of this, because you know it's got to come out as a quadratic, or it's a good check on your work. That's all. So it has a constant out in front, right? Now, what is that constant going to be? The constant can be any number, any number. Now, any number. We'll explore this more later. So any real number. Now, for us, the coefficients are always going to be real numbers. Any real number. It could be 2, 1 is a half, pi, whatever. Any real pi squared. Yeah, I know I'm making you feel a little under the weather there. Okay. Any number. We're just going to take the easiest number possible, 1. Why can I do that? Because it says find a polynomial function. It turns out there are infinitely many, and we'll look at that when we're done. We'll look at that in a minute. Just find one polynomial function that has these zeros. And there it turns out there's infinitely many, and we'll explore this after we finish. So I'm always going to take this constant to be 1. But just realize there is a constant there. I need actually the vertex if I'm going to come up with a unique polynomial. But they're not asking that. They're just saying find a polynomial function. Okay? So I'm just taking that constant to be 1. But it is there. It's just a 1. So this is the form I have. So I have x1 here. I'm just going to put that in there. 2. Now my x2 here. I'm going to plug that in there. Now just be careful with the sign here. Right? So it's x minus minus 3. Right? So it's a plus 3. Just be careful with that. It's an easy mistake to make, especially if you're on a test and you're a little stressed out. So just be careful. There I have it. Now I just have to multiply this all out. And this is just, look, it's just going to be a lot of distributed property. I know you could FOIL as whatever. First times that. Second number times that. And then it's just distributed property again. It's just a lot of algebra. So I'm going to take x times the x there, the x times the 3 over there, the minus 2 times the x here, and the minus 2 times the 3. And then you just clean it all up. That gives me x squared, 3x, minus 2x, and minus 6. Now mix up, put your other terms together, 3x minus 2x, and there you go. It's a polynomial. It's a second order. See, that's why I write P2. It's a check. It's x squared. All the coefficients are real numbers. Okay? And you can check. Do my zeros match up? Right? If I plug 2 in there, do I get 0? Yes. Right, it's a 0. If I plug minus 3 in there, do I get 0? Yes, check. So again, it's a good check. This is another problem where you can check your answer on the exam. Okay? So you're good to go. That's the basic problem. Now let's look at problems a little more complicated. Now let me talk about the constant. Now again, you can have any choice for A2. They just want one polynomial out of infinitely many. So what does A2 mean? Well, let's look at the picture. If I take A2 to be 1, this is what the graph looks like. Notice it has a 0 at 2 and a 0 at minus 3. And the vertex is what I need to get a unique. That's what makes it unique. All right, that's A2 is 1, is this one. Now, here's a different A1. If I take A2 to be minus 1, look, notice I have exactly the same zeros but a different vertex. And that gives me A2 is minus 1. Same zeros, but a different vertex. So again, this also meets the criteria. And you could take A2 to be minus 1. It just makes more work. Here's another one. A2 is 2. Notice I have exactly the same zeros. Exactly the same. That's all they want. Find a polynomial with those zeros. And the vertex would just be way down here. So A2 works. A2 equals 2 works. So since they only asked us to find one polynomial, we'll just take the easiest one with A2 equals 1. That's the idea. So here we're going to find a polynomial function of degree 2 having zeros. Now this is where the problem gets more involved. It's a polynomial degree 2, this one is 2. But notice my zeros in this case are complex numbers. The real part is so it's 0 plus 3i and 0 minus 3i. Now I want to point out, if you have a complex zero, they always come in twos. If you have 1, you have to get its conjugate, comes in the deal. Okay, so complex zeros always come in twos, in pairs. You have to get the number and its conjugate. Okay, so just be aware of that. They always come in twos. Sometimes in the homework they're trying to trick. I won't do it on the test, but in homework they're tricky. They'll only give you one, say 3i. Well, then they expect you to know minus 3i. For me, I think that's whatever. It's what we're dealing with. So they always come in conjugates and in pairs. But the problem is going to work out the same. It's going to work out the same. One of them is 3i, right? The other one is minus 3. I know there's 2 because it's a polynomial degree 2. And then, again, I'm just going to use the same. It's a P2 polynomial of degree 2. So I have to have an x squared term in it. I'm going to take my leading coefficient to be 1. You can take it to be any number you want. We're just finding any polynomial. But why not take it to be the easiest one? Right? So really there's a 1 there. And now I'm just going to plug in the data. Right? Plug in x1. Right? Just plug that in. Plug in x2. Again, be careful about your sign. I mean, it's an easy mistake to make. Okay? It's a plus. All right, now we just have to multiply it out. And this is where, I mean, again, I like the distributed property. It works for every possible case. It can get messy. So I take my x times this term, and I take my minus 3i times the whole other term. Okay, now I have this, and now I'm going to distribute again. The x times the x, and then the x times the 3i. It's just algebra. You just have to take your time. Minus 3i times dx, and then minus 3i times the 3i. Okay. Now notice I'm going to get an I squared here. Let's simplify. X times x is x squared, 3xi, minus 3xi, and notice I squared pops up. So I squared is minus 1. Remember, from the complex numbers, I squared is minus 1. And they're only going to have real coefficients. So I get a plus 9 there. And notice what happens with these. They cancel. They cancel. 3xi minus 3xi, they cancel. Because we can only have real coefficients. And that's a good thing. Don't look so. That's a good thing because our polynomial can only have real coefficients. If you get one of the coefficients like I in front of the x or 3xi or 6xi, it can't. We have to have only real coefficients. Okay, and that's it. And again, you can check your work. You might not want to, but just plug in. Right? 3 squared, I squared. I squared is minus 1. Right? So I'm going to get 0. So that worked out. And then you can check, it has to be a 0, and then you can check the other side. Okay? I mean, again, it's just a matter of how much you want to check your work. I mean, okay? Okay, now what if we have Now look, the difference here is I have polynomial degree 2, but I have zeros are full complex numbers, a real and imaginary part. So this just increases the algebra. It's just done the same way, but the algebra is more complicated. Again, notice they come in conjugates. Complex zeros have to come in pairs. They have to come in pairs. But it's going to work exactly the same way. Remember, it's not a bunch of numbers. It's a complex number. It's just a number. So my first zero is that. My second zero is the other complex number. Again, it's just a number. So again, I have the same formula. Look, it's the same formula. I'll take my constant to be 1, right? Why not? And it's exactly the same formula. So I'll just stick in x1 here, right? Just stick that in, right? Just be organized about it. It's just a number. You're sticking it in there. I have to substitute something for x2, right? Just plug that in there. I like to distribute the minus sign. Otherwise, I think it's a mess, right? So you put the minus sign in with the minus 2 and the minus 3i. Put the minus sign in with the minus 2 and the minus 3i, right? And now this is what you have. And you just distributed property. I mean, there are gimmicks you can memorize, this and that. Look, it's just distributed property. You're going to do how many of these in your life? Just distributed property. So take my x times everything in the back. Take my minus 2 times everything in the back. Take my minus 3i times everything. And now there you have it. You had to distribute again. I mean, it's just a lot of work. Take my minus x times my x. I mean, take my x times the x. Take the x times the minus 2. Take the x times the 3i. Yada, yada, yada. It's just a lot of work. Just a lot of work. Clean everything up, right? X times x is x squared, etc. Now look to cancel things and stuff. You have your I squared, right? Minus 1. So put that in there. Look to cancel things. Look, I have a 3xi here, a minus 3xi there. Cancel it. Bam. I know, that's great, actually. Minus 6i and 6i. Bam. No, it's not bad. It's a good thing. It makes everything easier. Look for it. And notice, clean it all up, and that's what you have. Notice there's no i's left. There's no coefficients that have I in it. Nice and clean. And you can check. Notice the coefficient is 1, minus 4, 13. Everything is real. I mean, you can plug these in and check. I don't necessarily recommend it. There's zeros. I did have a woman a couple of years ago who was a nurse, and she was desperate to get an A in the class. And she did. She worked it all out. I mean, that is really perseverance. But if you do plug them in, they do work, but I do think that's a bit of work when it's this complicated. I mean, that's a lot. Okay, so I mean, there's a lot of algebra there. And you can do it for 3, right? I have a polynomial degree 3. It has these zeros, 1, 2. I took minus 3. Yeah, I mean, it just increased the algebra level. What I want to point out is it's going to work exactly the same way. Here's my first one, my second one, third one. Notice if it's a degree 3 polynomial, 3 zeros. Only difference in what we've done is I use this form. I'm going to take my constant to be 1, and then I just substitute in to the same form here. Watch the sign. And then you just multiply it out. It's just more work. I'm not going to do it, but it comes out to this, I think. I did it, and that's it. And again, you can check your answer. It's just a lot of crunching away. I mean, it is. It's just the algebra goes on. Mind-numbing algebra. I mean, it just, yes. Okay, so what do you need to be able to do in this section? If I give you the zeros of the polynomial, you have to be able to construct the polynomial. So we're going from the local form to the global form. Okay? So those are the problems you need to do here. And you're just buckling down and do it. So that's what you need to come out of this section with. Okay? All right, guys. Good luck with that.